Example 20. Using the graph of f of x below, sketch a graph of k of x equals f of 1/2 x plus 1 minus 3. To make things simpler, we'll start by factoring out the inside of the function. F of 1/2 x plus 1 minus 3 equals f of 1/2 times x plus 2 minus 3. By factoring the inside, we can first horizontally stretch by 2, as indicated by the 1/2 on the inside of the function. Remember, twice the size of 0 is still 0. So the point 0,2 remains at 0,2, while the point 2,0 will stretch to 4,0. Next, we horizontally shift left by 2 units, as indicated by the x plus 2. Last, we vertically shift down by 3 to complete our sketch, as indicated by the -3 on the outside of the function. Horizontal stretch by 2, horizontal shift left by 2, vertical shift down 3. Example 21. Write an equation for the transformed graph of the quadratic function shown. Since this is a quadratic function, first consider what the basic quadratic toolkit function looks like and how this has changed. Observing the graph, we notice several transformations. The original toolkit function has been flipped over the x-axis. Some kind of stretch or compression has occurred, and we can see a shift to the right 3 units and a shift up 1 unit. In total, there are 4 operations: vertical reflection, requiring a negative sign outside the function, vertical stretch or horizontal compression, horizontal shift right 3 units, which tells us to put x minus 3 on the inside of the function, vertical shift up 1 unit, telling us to add 1 on the outside of the function. It is unclear from the graph whether it is showing a vertical stretch or a horizontal compression. For the quadratic, it turns out we could represent it either way, so we'll use a vertical stretch. You may be able to determine the vertical stretch by observation. By observation, the basic toolkit function has a vertex at 0, 0, and symmetrical points at 1, 1, and negative 1, 1. These points are 1 unit up and 1 unit over from the vertex. The new points on the transformed graph are 1 unit away horizontally, but 2 units away vertically. They have been stretched vertically by 2. Not everyone can see this by simply looking at the graph. If you can, great. But if not, we can solve for it. First, we will write the equation for this graph with an unknown vertical stretch. F of x equals x squared, the original function. Negative f of x equals negative x squared, vertically reflective. Negative a f of x equals negative ax squared, vertically stretched. Negative a f of x minus 3 equals negative a x minus 3 squared, shifted right 3. Negative a f of x minus 3 plus 1 equals negative a times x minus 3 squared plus 1. Shifted up 1. We now know our graph is going to have an equation of the form g of x equals negative a times x minus 3 squared plus 1. To find the vertical stretch, we can identify any point on the graph other than the highest point, such as the point 2, negative 1, which tells us g of 2 equals negative 1. Using our general formula and substituting 2 for x and negative 1 for g of x, negative 1 equals negative a times 2 minus 3 squared plus 1. Negative 1 equals negative a plus 1. Negative 2 equals negative a. 2 equals a. This tells us that to produce the graph, we need a vertical stretch by 2. The function that produces this graph is therefore g of x equals negative 2 times x minus 3 squared plus 1. Try it now. Consider the linear function g of x equals negative 2x plus 1. Describe its transformation in words using the identity toolkit function f of x equals x as a reference. Example 22. On what intervals is the function g of x equals negative 2 divided by x minus 1 squared plus 3 increasing and decreasing? This is a transformation of the toolkit reciprocal squared function. F of x equals 1 over x squared. Negative 2 f of x equals negative 2 divided by x squared. A vertical flip and vertical stretch by 2. Negative 2 f of x minus 1 equals negative 2 divided by x minus 1 squared, a shift right by 1. Negative 2, f of x minus 1 plus 3 equals negative 2 divided by x minus 1 squared plus 3, a shift up by 3. The basic reciprocal squared function is increasing on negative infinity, 0, and decreasing on 0, infinity. Because of the vertical flip, the g of x function will be decreasing on the left and increasing on the right. The horizontal shift right by 1 will also shift these intervals to the right 1. From this, we can determine g of x will be increasing on 1, infinity, and decreasing on negative infinity, 1. We also could graph the transformation to help us determine these intervals. Try it now. On what intervals is the function h of t equals t minus 3 cubed plus 2 concave up and down?